So I'd like to talk about this joint product, as I told you, that I'm working with Sergei concerning the Gilles Pisier approach to Poincare-type inequalities, and in particular to some generalization that we try to obtain in this field. So I prepared just a few slides because I didn't want to be too much technical. I want to introduce you a very simple problem. So how to generalize this. Let me see, maybe there's a problem here. Yeah, I mean, this is the plan of the talk. How do I...
Chandra, we might need your expertise on how to do the slides.
Just control L.
Control L?
Oh, okay. Thank you very much. Thank you very much. And so this is the plan of the talk. So this is the introduction of the Pisier's inequalities approach to Poincare-type inequalities. And then the second part is devoted to generalization to this approach to general measures. So how? And the third part is concerned basically about the application of some isotropic measures. And the fourth part will be concerned about the application of some spherical invariant measures, so very special measures. So let's start with the classical Pisier approach to the study of Poincare-type inequality, which concerns, as you most of you know, the Gaussian case. So gamma n denotes the classical Gaussian density. So we work with Gaussian measure. And in this very classical paper by Pisier, he obtained the following very interesting integral differential inequalities in this way. You see, when C is a common function, and for any smooth function f on Rn, you obtain this Feldman inequalities, which in particular gives as a direct consequence this inequality right here by using Jensen. This is contained in a very classical paper by Pisier. So let me mention that there are in the literature many some extensions of this approach. In particular, let me mention this paper by Sasha, who was present here in the audience, concerning this study of this approach to the discrete. Okay, I thought that it would be interesting to recall the proof of these inequalities, which I found really magic, and my point of view, really direct. So just a few lines to explain you how the proof comes out. So you take just two random vectors, independent random vectors, standard random vectors, so with distribution gamma of n, and then you take this path, which is the random vector connecting the x with I, where d is between 0 and pi half. Then you study the fluctuation of these two random variables under a certain function, as a smooth function f, and you write this difference by its own integral, and then you apply the Leibniz formula, and you obtain this. Very easy. Where this is where x prime is the derivative of this path, and now you apply Jensen inequality. And of course, you have by applying this inequality, you have to apply to a probability measure. You have to divide by half, and now you take the expectation. Okay, you take the expectation with respect to Gaussian measure. Of course, the expectation here is taken on the Gaussian measure of dimension 2n, and then now the observation here is really, you see, x and x prime. You can consider in the plane as a rotation, and then you know that say by using the rotational invariant of the Gaussian measure, you actually have that x and x prime is an independent copy of x and y. So by using just the rotation invariant of the rotation invariant property of the Gaussian measure, you have that the integral here, the right-hand side, does not depend on t. And then you obtain the main inequalities. You have here you can replace x and x prime by x and y, and that's how the inequality comes out. It's really magic, and it's used of the fact that heavily used the fact that the Gaussian measure is really a particular measure, which is in particular rotation. You see that the main inequality obtained by Pisier, yes, you can take, for instance, in the case where the constant function can be chosen like r to the p, and you can write the Poincare inequality in this form. Yes. Yes.
Just as a small historical remark,
yes.
Pisier indeed proved this inequality, but his first proof was using expansions along Hamilton polynomials.
And then it was simplified.
The proof that you presented was communicated
by Moret. Sorry. Yeah, the simplification is due to Moret. Yes. So, yeah. Yes, I apologize for not making this remark. Thank you very much.
So it's on Moret's approach, you mean?
It's on Moret approaches. Yeah, that's the simplification of the original Pisier approach. Yes. So if we take this special case here, you have the appearance of the constant here on the right-hand side, which I call Cp, which is actually dimension-free. You can calculate explicitly. You can use Jensen inequality, and you can write the same inequality in terms of the average, and you can calculate explicitly the constant appearing on the right-hand side. Even though the constant is not optimal, at least for one case, for p equal 1. For p equal 1, you obtain that the constant c is a sharp constant in this Gaussian isoperimetric inequalities, and for other cases it is not sharp. But as you can see, it is dimension free. So still, you have the sharp case only one, for one choice of the constant. Otherwise the constant is a little bit rough. So our aim that we try to study with Sergei is a generalization to this approach to other measures. And following the same lines of the proof used by Pisier, by Moret. So we take in this case a general measure mu, positive Borel measure mu on Rn times Rn, and we take a smooth function f on Rn, and we can compute the fluctuation of this difference under the action of the measure mu. So we do this way. And we consider the path connecting x with I. So and then we do more or less the same as the Moret's approach of the Gilles Pisier inequalities, and we arrive here like before. And now we take any convex function psi, and we use the Jensen inequality. We arrive here. See. So and now we take the integration. So with respect to mu, double integration with respect to mu, and we have here. So no difference up to now. But now we're going to consider mainly the same linear transformation, orthogonal transformation used in the main approach, which is a rotation, if you consider it in the plane. And then you can write, the right hand side of this inequality in this form here, where I call H, this decomposition of this function psi times this scalar product. And then here now you can replace mu by mu t, which is just push forward of the measure mu under the linear transformation ut. Okay, and now you call mi hat the measure of this family of a measure of mu under the orthogonal transformation that I introduced here, and so you can write the final inequality in this form. We will call this new measure of mu hat as a spherical cap, because as you see, it's an average. It's an integral average of mu under this orthogonal transformation, in particular in the plane there are rotations. And we will see in a while some of the main properties of this new measure mu with some examples. So I anticipate this. We don't have the clear framework, the whole properties concerning this new measure mu hat. But I'm going to say more in a few slides. So far we obtain this generalization that we can state in the main theorem, which was obtained with Sergei. So for any positive Borel measure mu or the product of Rn times Rn, and for any smooth function phi f, and for any complex non-negative function psi, we obtain this let's say Poincare-type inequality in this form. Then, of course, if you have that mu have a certain density depending on the two variable x and y with respect to the measure, it is rather easy to check that the measure mu t, which is the post-square forward of mu under the action of the linear transformation capital mu t, has this density here written here, which is a composition with the inverse transformation of ut, the inverse rotation, and then what you obtain as the end is that this new measure mu hat, which we call the spherical cap of mu, has the density written in by means of this integral here. So you can restate and you can reformulate this main theorem in terms of densities. So you can replace the main measure mu by this density w and w hat. And then in particular, of course, if you take any power p, you can write the inequality here in this form. As you can see, the main we have some aspects that we have to underline. We don't have so many properties concerning the measurement during the new measure mu hat, but still the right hand side we use a constant which appears on the right hand side is dimension free. So some examples, we have some examples concerning the explicit computation of this measure mu. That is really worth to make a remark. As I told you, we decided to call this measure as a spherical cap, according to how it is introduced. It is a kind of measure which is more rounded than the first one, and it somehow is closer to a class of spherical invariant measures. So that now that the examples that I'm going to tell you gives in fact the spherical invariant measure. So the explicit computation that I'm going to show you gives the explicit form of mu hat as a spherical measure. Of course, some properties. If mu is a spherical invariant, then mu hat coincides with mu. That was for instance, the case of the Gaussian measure. This is really a trivial observation. But now we take this more interesting remark under my point of view. You take a symmetric Bernoulli measure nu, which split mass between 1 and minus 1, and you consider the product measure of nu by itself, and then what you obtain is this measure, which is concentrated on the vertices of the discrete square. Okay. Then when you compute mu hat, what you obtain is this can be done as an explicit computation. You have these vertices of this discrete square. What you obtain in the end is the normalized Lebesgue measure on the circle of radius radical 2, or square root of 2. Well, this can be done just by observing how the measure V hat is defined, because the measure V hat is defined as the average of the rotation of the actional rotation of the measure mu, and you see that the mass is concentrated at beta thetas in these four vertices of this. So you have to make the rotation up to an angle pi over 2, and that's how this new measure comes out as being right, the Lebesgue measure concentrated on this circle. So the Lebesgue measure restricted on the circle of radius radical 2. So this is so you can do it rather easily, and this is for the discrete case. For the continuous case, it is the calculations are a little bit more advanced, more involved, I would say. If you consider the Lebesgue measure on the normalized Lebesgue measure on the continuous square on the square, then so in this case the density is given by 1/4, and then you can compute explicit the density of this new measure mu hat, and it comes out that it has this form here. It's radially symmetric, and this as you can observe, the support of W hat is still on a circle of radius square root of 2. So in both cases, you have the support of this new measure is larger than the support of the original one. Okay. We don't know. So these are very I would say very particular examples that is worth that I think it is worth to mention. So in both cases, the measure that you obtain is spherically symmetric. But the framework is still a little bit unclear for more general measure. So then we can skip to the application with isotropic measures in the sense that I'm going to describe you in a few slides. So we take in the main inequality the complex function as defined as the square root of t, and then you obtain this, okay. And then what we want to do is to give condition in particular on the measure mi hat in order to simplify the right hand side. Okay, so this is actually the most difficult issue to solve in this under this point of view. One thing that you can let's say one approach that you can use is just just try to decompose or use this integration measure of this new measure method by conditional measures which are supported on slides. So usually you remember I recall here what I mean as this integration measure. If we take any finite for a positive measure mu, defining on Rn times Rn, and we take the first marginal, which is called P pi, as a projection of the first coordinate. Then you take, by the classical disintegration measure theorem, you take this called the decomposition of nu in terms of the conditional measure of nu and nu u with respect to the first with respect to the projection of the first coordinate, the first marginal, and all of these measures are supported on this hyperplanes, right? And another way to write this result is you can write in the integral form by taking any measurable function. You can assert this result also in the integral form. So you can use this integration theorem by decomposing mu hat on the right hand side. And you arrive from here to here. And now, how to simplify this? You say that you have an integral on Rn of the square of this scalar product with respect to the conditional measure. So one way to simplify this is to give some assumptions on the measure mu hat in order, for instance, to put the gradient outside of the integral squared, right? And by the way, we will need the integral which remains does not depend on unit vectors, or vectors of unit normal with respect to the angle. That's actually the definition of isotropic measure. So that's why we use here this way to write down the right hand side of this inequality by using the classical definition of isotropic measure. But it's different in this setting because here we the assumption that we make is to assume that the measure we had and the conditional measure we had are isotropic. So it's like saying that this new measure is isotropic with respect to the first coordinate. So it's like saying that all the conditional measures are isotropic. And the condition of isotropicity is written here. Of course, you have the appearance on the right hand side of a certain constant depending on u. Okay. So assuming that you can do this, then the right hand side of this inequality can be written in terms of the isotropic function, which are called sigma hat. Sigma hat of u is the isotropic function associated to mu hat. And that's with respect, of course, to the first marginal, to the projection of mu hat on the first coordinate. So that's then you can write the main inequality also in this way, okay? And then what you get in this form, you get a new weighted Poincare inequality where the weight is represented by the isotropic functions, associated to the new measure. Okay, so just to give you examples of this approach is the first example that we want to mention is from now on I will show you some examples concerning all the spherical symmetry measures. Some real applications of this approach, in particular in two cases. In the first case that we are going to discuss, it concerns the uniform Lebesgue measure on the sphere of dimension 2n minus 1. Yeah, I mean the inequality that we have in this way is written in this form because you have that mu is spherically invariant, and you have mu at the left hand side and the right hand side. So take for instance the convex function psi is the classical square power of t. And we take as one of the examples that I'm going to discuss is the uniform distribution of the sphere, the unit sphere. So recalling that we have to obtain the form of the conditional measures of mu. We have to compute the sections on this on the sphere under just the vertical section of the sphere, and what you finally obtain that these sections are just given by this, each section is given in this form, so they're just spheres, there's just sort of spheres of radius for x a fixed x, for radius square root of 1 minus x squared. So what you obtain in the end is then the conditional measure of mu is given by the uniform distribution of such spheres. Okay, because of the fact that the main measure is rotationally invariant, and by the rotational invariant, you give that the conditional measures are given by the Lebesgue uniform distribution of this convex n minus 1 dimensional sphere of this radius. So you can plug everything in the main inequality here. And what you obtain is that since you have that these conditional measures are of course isotropic, what you can obtain is the calculation of the isotropic function. You are on the sphere of radius square root of 1 minus x squared, and so this is the explicit form of the conditional of the isotropic function defined on the ball of radius 1. Okay. But actually, you can also find the marginal measure of so the projection of the initial measure on the x coordinate, and by using some let's say using some efforts and some computations, actually gives you that the density of this of the first marginal is given by this power of this function here up to this constant appearing in front of the powers. And so that's how then the inequality takes form. In this case of the uniform distribution of the sphere, that our approach gives this inequality here. And in particular, this inequality is rather similar on this Poincare-type inequality on the ball. And on the right hand side, you see the appearance of the constant depending on dimension. And this second inequality, which is a little bit similar to the first one, was obtained in this paper by Sergei in 2003. Yeah. What else can be said for the inequality that we obtain for the uniform distribution of the sphere? Yeah, I mean, if you in terms of concentration, for instance, if you consider Lipschitz functions with having Lipschitz constant less than 1 or unit Lipschitz constant, you obtain that the integral on the right hand side can be explicitly computed, and you obtain this estimate that it might have some interest on the lower point of view. Now what we are going to discuss is just the last, I would say, the last part of my talk will mainly concern the application of our result to a particular measure, which is called Cauchy measures. And so the Cauchy measures are measures having this particular density here, and in order to have a probability density, you have normalized with respect to this to a constant which is having this explicit form. And in order to have the integrability, the right integrability, what you have to consider is the order n alpha larger than half of the dimension. Okay, this kind of measures are particularly important because some inequalities and some results that can be obtained in this setting can be seen as pre-Gaussian, in the sense that some results obtained for the Cauchy measures gives you the chance to obtain, let's say, the similar results in the limit for the Gaussian case, because by using this scaling here, so considering the image of the Cauchy measure under this transformation, what you obtain is that the new Cauchy measure has this density, and when you pass the limit as alpha goes to infinity, you recover the Gaussian density. So in some sense, you can see the class of Cauchy measures as a pre-Gaussian model. Okay. So by using this scaling, you let alpha goes to infinity, and you recover the Gaussian density. Under my point of view, this inequality, Poincare-type inequalities associated with this kind of measure is rather popular in literature. And by the way, this is very, very important also in the field of the PDEs that I'm going to mention in a while. And for this Poincare type inequality, the constant here at the right hand side depends on the order, not the dimension, is known for any alpha larger than half. And this family of inequalities are called Hardy Poincare inequalities because, as I told you, the scaling that before allows you to obtain the Gaussian Poincare inequalities, but there's also another scaling give you the chance to obtain the Hardy inequality. Because in literature they are called Hardy Poincare inequalities for this reason. And this kind of inequalities are very, very important because they can be used in particular. That's how I saw the connection with PDEs in the study of the asymptotic behavior of solution to certain nonlinear diffusion equation in this form. And when you see that you see here the nonlinear diffusion given by a power of m, when m is less than the 1, this nonlinear parabolic equation is called the fast diffusion equation. It's different with respect to the case m larger than 1, when you and in that case this equation is called the porous medium equation. Where is it the connection between this family of inequality and this equation? The connection is given by a function of this type, which write the self-similar solution to this equation. So the fundamental solution of this equation in this regime, and so you see that this is a particular case of the Cauchy measure for this choice of this exponent. And these inequalities can be used, as I say, in particular to the study of the asymptotic behavioral solution of this equation towards the Baron-Blatt profile by getting in particular the best rates of convergence. So this family of inequalities are very important in this field. This is collected in a series of papers. Of course, there is a very important paper by Michel and Sergei, in which they studied, among other results, the same family of inequalities, and it was the aspects connected with the asymptotic fast diffusion equations were obtained in this couple of papers here, in which independently with respect to the first one, they were able to find the right form of the Weiss constant here, which were essentials for the study of the asymptotic behavior. Okay, this is what just a little remark concerning some literature, some papers connected to literature. And what I'm going to study in our approach is the Cauchy measures of R to the 2n, so Rn over An. So we consider two n-dimensional Cauchy measures on the product of Rn times Rn. So in this case, you have the density have this form here. Of course, in this case, you must have that the order alpha must be larger than n. And then we want to apply our inequality to this measure. Of course, you have these measures are rotationally invariant, so you have the appearance of the same measure on the left-hand side and on the right-hand side. For instance, we take the complex function as p power of t. And so you arrive here, and you want to give some information on the right hand side to compute it explicitly. So just I will give you some hints about some simplifications of the integral on the right hand side. You write the integral on the right hand side in this form. This is the classical normalization constant of the Cauchy measure. I call dp this integral here, depending on v, and you put v to the power p, the modulus of v to the power p out, and you call dp x theta as the integral coming out, which depends on x and on the angular coordinate. And then what you observe that by the spherical invariant of the Lebesgue measure, you obtain that this integral coincides with the expectation with respect to the angle, and then you can put the expectation inside here. And what you finally get, since you have the homogeneity of the Lebesgue measure and the rotational inversion of the Lebesgue measure, again you can extract the power of y here times so you can write the expectation of the respect to the angle in this form, and for some constant g and p, which can be computed, by the way, explicitly. You take a unit vector, and what you finally obtain is that the constant is just the expectation of respect to the angle of the first angular coordinate. I don't want to bore you so much concerning the computation of the constant. Here you can compute it explicitly. And what you finally get is that the constant can be written in this form in terms of gamma function. So you can actually what you get is that this integral can be written in this form here, and then by making extra computation what you finally get is that this integral can be written in this form. And you have the appearance of this weight outside times this integral here, and now you see that in order to have it in integrability, you must assume this restriction on the exponent. Okay? So far so good. Now what we want to, now this integral here can be written, how to go behind, yes. And now you can compute explicitly the integral here on the right hand side, and so the explicit computation gives this exact form of a p. Okay, very good. Where the constant is this ugly guy here in terms of beta function and so on. And finally, by using this expression of PEP, you arrive finally at this form of the right hand side of the Poincare inequality with this constant here. I called and you see the appearance of the Cauchy measure with respect to with order beta. Beta is alpha minus n plus p over 2. And in order to have an integrability condition, you must impose that beta is larger than n half. Okay? And so what you obtain at the end is, as a consequence of our inequality, is this inequality with this condition of alpha and of p. When alpha is larger than n plus 1 half and p is less than 2 alpha minus n, which is the condition that I explained you before, coming from the integrability of the weight, you obtain this Poincare-type inequality. You don't have the same weight on the left hand side or the right hand side. You see, you have a weight. You have the two-dimensional Cauchy measure of order alpha. And n-dimensional Cauchy measure of order beta. The orders are different, but you have a constant here which is explicit. It's even in this form. But still, if you make a scaling like the one that I showed you before, what you recover in the limit, you have you can write the main inequality in this way here. And letting alpha goes to infinity, what you recover is the P Poincare inequality for the Gaussian case, with the same constants that I showed you in the first slides. So this is rather coherent as one would expect. You see, we don't have the same. I want to insist, we don't have the same order at the left hand side or the right hand side, but asymptotically, you get the same inequality. Okay, this is interesting under our point of view. So you obtain the optimality under this point of view. Now we want to see the connection with respect to isoperimetric inequality. As you know, the isoperimetric inequality is rather connected to the Poincare type inequality for the case p equal 1. Okay, for p equal 1. And so you for the Cauchy measure you write down inequality the main inequality in this for this choice of p for p equal 1, and what you actually you can also make some simplification in order to get rid of the gamma function on the right hand side here. In particular, you can bound this ratio which appears on the right hand side by considering sufficiently large alpha in this way. If you want to get rid of the gamma, the equation that this gamma function is. Okay. Yeah, I mean, as I mentioned you by the same scaling that I mentioned you before, you obtain the passes to the limit. You obtain the L1 Poincare inequality, giving you in this case the sharp constant for in the Gaussian Poincare inequality. Of course, this sharp constant is achieved on half spaces whose boundaries pass through the origin. Okay, and the optimal function is the indicator function of such half spaces. So we want to see right now the connection between this inequality and the isoperimetric inequality, and so we consider the range where the alpha is larger than n plus 1 in order to get rid of the presence of the gamma ratio of the gamma function to the right hand side, and what you actually can prove that this inequality is in fact equivalent to a certain type of isoperimetric inequalities connected with these two measures. In particular, what you can prove, actually it can be proved in general. For general measure defined on the product of Rn times Rn and on Rn. Once you have this inequality, you have that this isoperimetric inequality holds where the perimeter in the sense of Minkowski constant. Okay. This comes out from a more general information that you can obtain by inequality which is written in this way. This isoperimetric inequality is valid for any closed set in Rn. And now, if you want to further simplify it, further obtain a more familiar way to see the isoperimetric inequality, what you want to get is some bound of the Cauchy measure on R2n of order alpha by the product of m of the Cauchy measure of the same order but on Rn. Let's say, is it possible to see by making suitable computations that it's possible to bound this measure by the tensor product over mn alpha times mn alpha, and up to a certain constant which can be written explicitly in this form. And then you see, you replace this guy by the tensor, the product measure here, and you can rewrite the isoperimetric inequality in a more familiar form. Okay, this is the isoperimetric inequality for the Cauchy measure that we obtained by our approach. You see still that the order of the two measures are different on the right hand side and on the right hand side and the left hand side. Sorry, how many minutes left?
We have 10 minutes.
10 minutes more. Okay, that will be sufficient. Yeah. Now let's say something concerning the moderate and large deviation. It's as you certainly know that they can be derived from general Poincare inequalities for a general exponent p that I repeat here. What we obtained so far is this inequality with this restriction of the exponent, when the constant here depends on np and alpha in this form. What we want to study is in the case of if you want to study the larger division, you have to consider the case when f is the Lipschitz constant for f is less than 1, and once you have this, the previous inequality can be written in this way. And what you want to obtain then is to study the probabilities of moderate and large deviation of this different under the action of the Cauchy measure of order alpha on Rn times Rn. And yeah, I mean you can further simplify the right hand side by further assuming that in particular for this kind of exponent, this kind of choice of the exponent p, that you can get rid of the presence of the gamma function, and you can you have the right hand side appears in this form here, where with the explicit presence of the probability exponent here, where the constant c is pi half pi square over 4. And now, if you want to consider the fluctuation of fx minus fi under the action of the probability measure m2n of alpha, then you consider the measure of this upper level sets of this function of the product of n times Rn up to this factor square root of alpha over n, because you see this presence of the same constant here on the right hand side. And by using Markov inequality, you have that it is possible to see that the estimate of this function can be obtained in this form. You see that you have a moderate Legge deviation concerning different choices of the intervals. So when t is between 0 and t0, where t0 is given by the square root of alpha over n, you have an exponential decay. You have when t is larger than t0 and less than t1, you don't have any exponential decay. When t is larger than t1, you have an algebraic decay. But you can obtain similar expression when you bound the measure m2n alpha by the tensorial product, tensor product of the same measure mn alpha times mn alpha. And so analogous relations for similar regions can be seen, and it's actually sharper. And it was obtained by Michel and Serrier in this paper on anal probability on 2009. So I think that I just gave you some implications of the approach that we obtained in the paper with Serrier concerning this kind of generalization of Pisier approach for general measures. So they said there's still a lot of work to do, but yeah, I mean, some open problems, as I told you. The framework is not clear in the more general case. So one of the first point it would be to study more properties concerning this new measure as may have with what we call the spherical cap. In particular, to give more examples concerning this, and because you see that the only thing that one have at the moment, we know that. In principle, when you start from a certain measure mu with a certain support, you get a measure mu hat which is more rounded than the mu, and it has some symmetries, but in principle the support is larger. So how to compare mu to mu hat? This is not clear in principle. So to study more further properties concerning the connection of mu and mu hat and apply it eventually to the Poincare inequalities that we obtained. And yeah, I mean, more explicit example could be in order and be really important for this kind of approach. And so I think that I can stop here. I hope that you found some interest in this this bunch of results that I showed you. So I think I can stop here. Yeah, I mean, generalized also the Pisier approach in the discrete setting would be really great. So this we didn't even start in that direction, but it would be really great under our point of view. So thank you very much for your attention.